The week 6 material is all about circulation of the atmosphere and then circulation of the ocean. It's a really important subject as far as oceanography is concerned, but you'll notice that this note set is actually rather small. That's because there's just a few key points in the whole notion of circulation in these two domains that I really want you to get, and I don't want you to be bogged down with a lot of extra surplus information. So this note set is concise. The narrated lecture is even more concise, and you'll see I've trimmed the readings down as well. Okay, first of all, recall that there is this phenomenon that we call the heat budget, such that at the lower latitudes, the tropics, if you will, on either side of the equator, there is a surplus of heat. And then in the temperate and high latitudes, there is a deficit. Because of this inequality, there is this constant, steady transfer of heat from an area of surplus to an area of deficit, basically from the tropics away towards the poles. That is done by both wind and air, and that's why we have to talk about circulation in both domains. So first of all, for winds, we're just going to give a very, very, very brief introduction to this whole topic here, only as far as how it controls oceanic circulation. If you're interested in this subject, well, this department, Geography, Geology, and Environmental Sciences, teaches several courses that are climate-specific, where the atmospheric phenomenon are emphasized, and that's where you should go if you're really interested in those things. Okay, there is a convection cell model that operates once again, but here for the atmosphere. So recall for plate tectonics, the convection cell was transferring heat from the center of the Earth to the surface, and that moved the plates around. Same dealio here, hot air in lower regions of the atmosphere and in lower latitudes rises and then spins, and it results in a transfer of heat away from the equator. If you look at the diagram, there isn't just one large convection cell that kind of rises at the equator and travels all the way to the poles and comes back. Because of the mathematics of our spinning Earth, there end up being 3 of these convection cells. So notice in the equatorial region, there is this rise of hot material. It circulates up in the atmosphere, and then it drops at about 30 north and also at 30 south. Keep that in mind. That is the reason why those particular areas, 30 north and 30 south, are among the driest on planet Earth. That's where the bulk of Earth's large deserts are, because it is constantly being bathed by dry air that has been rained out in the tropics. It comes back down as dry air. The transfer of energy to water is accomplished by the winds blowing over the ocean. Remember, the oceans cover 3/4 of the planet, and the winds cover all of the planet. They're blowing over the oceans, transfers energy to it. Just as if you blew on the top of a coffee cup, you can see you create ripples and motion in the coffee cup. The same thing happens here. The transfer is very, very small, though, 1 to 3%. And so as it says there, just as an example, a 60 km/h wind is only going to produce at most 2 km/h ocean current. If you look on the diagram, the red lines are denoting the predominant wind directions. And so in the northern hemisphere, we have the westerlies, and then in the southern hemisphere, we have the trade winds. And the red lines of wind produce the large green lines of water motion. The density of water is much, much higher than the density of the atmosphere, over 1,000 times. And so it's a little bit different. What happens is once water is in motion, it tends to stay in motion. So the wind, you know this, it can flop and back and forth and come from the south, come from the north, come strong, it can change daily, it can change hourly, but the inertia of the water is such that the prevailing, predominant wind directions create ocean currents that stay in constant motion, reflecting the prevailing pattern. So ocean currents respond to long-term forcing, not daily switching and changing. Another important feature of the ocean to wind interaction is that there is a change in the direction of water transport versus wind transport. Look carefully at this diagram. We've got the wind direction shown as this prominent blue bar. So let's say the wind is going directly due north. Let's pretend that's due north. The surface of the water doesn't also sort of cook along at due north. It is shooting off at an angle of about 45 degrees from that direction. It's given that it's just the way the forces operate when you have this low density, high velocity fluid moving over this much higher density, much slower moving fluid. The surface currents then influence the water below them, and that is also offset. Deeper still, let's imagine that every one of these is 10 meters deep. Go another 10 meters deep, and it's offset again, another 10 offset, another 10 offset. At some point, you actually reach a point in the water where the wind can be blowing due north, and the force that it's operating as it is projected into the deep will actually be moving water in the exact opposite direction. If you sum all of these vectors, though, you get this giant, large, three-dimensional arrow of the net transport of the water. So, go back one slide. Notice that the westerlies, these, let's just as an example for the northern hemisphere, wind is blowing in that direction, but notice that the net water movement isn't going in the exact same direction. It is offset to the right in the northern hemisphere. There is something else called the Coriolis force, and this is a little bit of a more complex thing to understand, and if you really don't, that's not so terribly important for this class, but realize that if you have an object traveling over the Earth that is spinning around, then the Earth will spin out underneath that moving object. It's much easier to imagine or think about for a flying airplane, let's say. You know, if an airplane flies due south from point A to point B, the Earth moves under it so that the Coriolis force makes it such that the path of the airplane is curved to the right direction. The water does this as well. Ocean currents are moving above a spinning Earth. It's harder to imagine that, but they are, and they are also forced to the right. This, of course, is the opposite in the southern hemisphere. Now, these things make these features that we call the gyres. If you look at the interaction of the Coriolis force, this veering to the right in the northern hemisphere, and these pesky continents that get in our way, you end up creating a series of gyres. These sort of, and a gyre is just a circular moving path of a fluid over an object. And so we have currents that are moving, my cursor seems to be moving on its own, always to the right of the winds, creating the Gulf Stream, Atlantic current that runs into the pesky European, African continents, and so the deflection is to the right, hits the land, so it travels south as the Canary current. There, it starts interacting with the trade winds, which also deflect to the right, creating this north equatorial current, which delivers the water back to the Caribbean Gulf of Mexico area. So notice that there is this roughly circular pattern of water in the North Atlantic. Every gyre is similar to this in that there are equatorial currents produced by the trade winds. There are western boundary currents, and these are deflected northward and eastward by the Coriolis, and then there are the eastern boundary currents over here. If you then look at the globe, there's the North Atlantic. We still have the gyre that we used as our example, but look at the North Pacific. There's the same thing. The Kuroshio current becomes the North Pacific current, the California current, and then the equatorial current return. In the southern hemisphere, it is the opposite, and there is the Pacific gyre, Southern Pacific gyre, the Southern Atlantic gyre, and then the Indian Ocean gyre. So northern hemisphere has 2 prominent gyres, southern hemisphere has 3 prominent gyres. This Coriolis force and gyres has this constant rightward deflection as you go, so this creates this lens, like it says here, of accumulated water in the center. It literally will build up small hills of water such that, I mean, we're used to thinking of sea level as being flat as a table, plain, all the way from one beach on, say, the Atlantic North American coast to some beach on the European Atlantic coast. But because of this forcing, there's actually a bulge, 1 to 2 meters, and I've seen some estimates where it's as high as 5 meters. So the height of the water, because it's being constantly pushed inward and upward, creates a bulge. The water then falls down. That's this opposite, this FG, because water doesn't stack up continuously as an equal and opposite force to the Coriolis that way. Remember that it creates this bulge. The bulge isn't perfectly symmetric. It is offset. The western currents are much, much stronger than the eastern currents. And so the buildup of this hill is higher towards the western sides than the eastern sides. So again, look at this diagram. It's not a perfectly symmetrical circle with a nice little bump in the middle. The bump is offset towards the west. Before I talk about countercurrents here, again, look at this diagram. The bulges, and I'm talking about the northern hemisphere now, are offset towards the west. So this hill within the central North Atlantic has been pushed and offset by a couple hundred kilometers towards North America. In the North Pacific, the bulge has been offset quite a few hundred kilometers towards Asia. Again, in the southern hemisphere, the effect is the opposite. There are also these odd little currents called equatorial countercurrents. So yes, this water piles up, there's extra water on the western sides, and as it falls down, and it literally sort of fills the gap between the 2 humps of the northern and southern hemisphere gyres, and it will flow the opposite direction. So this is a cartoon showing this. The orange arrows are the equatorial countercurrents, and then the lower figure, you can increase its size and look at it on your computers, shows the various vectors of equatorial or flow of water, and you can see that there is this surprise deflection in the opposite direction, this equatorial countercurrent. The currents of the ocean are a very important feature. They're going to become very important for us when we actually talk about the biology of organisms, whether they are large organisms or even the smallest things, plankton, which are at the mercy of these ocean currents. But the distribution of these currents has probably one of the most profound effects on the distribution of life on Earth. For now, I just want you to understand why they exist, how they exist, and a few of these odd features: Ekman's spiral, Coriolis force, Western intensification, and the countercurrents.